Hello everyone, welcome to Engineer. Today we'll be discussing on this topic of prestressed concrete and we'll be solving MCQs and some problems as well. Let's see. So before solving some MCQs, let's see a basic about the prestressed concrete. So the basic concept of prestressing the concrete consists in introducing the artificially compressive stress. So introducing what? Introducing compressive stress. So the tensile stress in the prestressed concrete structure may be reduced to a great extent or even entirely eliminated depending upon the magnitude of prestressing. So why are we introducing this compressive stress? So to counteract tensile stress, right? Counteract tensile stress. As we know, concrete is very weak in tension, so we need to counteract this. So we are introducing what? Compressive stress into the structure. So again, in a prestressed concrete structure, the cost of supporting structure and a foundation is reduced. So cost of supporting structure and foundation is reduced, dead load of structure is reduced, and cracking of concrete is avoided. This is also important here. This is important here. This is important here. And the high strength concrete and high tensile steel should be used in the prestressed concrete member. So this is very important. So high is for in this with respect to MCQ, this is very important line. The high strength concrete and high tensile steel should be used in a prestressed concrete member. According to Indian standard, the cube strength of concrete should not be less than 35 Newton per mm square. So it should be greater than 35 Newton per mm square. So the ultimate tensile strength of high tensile steel wires used in the prestressing varies from 1500 Newton per mm square for 8 mm diameter to 2350 Newton per mm square for 1.5 mm diameter bars. So we need to use high strength concrete as well as high tensile steel wires, right? So if we use low tensile stress wire, then the loss of prestress will take off all this strength of the wire. Let's go to the next slide. Okay, the question here is the question. The prestressed concrete induces artificially what? Artificially compressive stress, right? We already talked about this. So this is compressive stress. So you can see here the main principle of prestressing a concrete member consists of inducing sufficient compressive stress, right? Next. Okay. So in a prestressed concrete structure, dead load of structure is reduced. Yes, it is reduced. Cracking of concrete is avoided. Yes, and the cost of supporting structure and foundation is reduced. So our answer is all of these above. So you can see here. So if we see 3 number here, prestressing eliminates the cracks in the concrete under all stages of loading, right? And next is it reduces dead weight of the superstructure and also saves the cost of foundation, right? And also there are different advantages of prestressed concrete. You can read here, right? So let's go to the next slide. So our answer is all of the next slide. In a prestressed concrete member, so we already talked about this, right? So we need to have high strength concrete and high tensile steel should be used. So in order to get the maximum advantage of a prestressed concrete member, it is necessary to use not only high strength concrete but also high tensile steel wires. So the ultimate strength of the steel used for prestressing is nearly 1500 Newton per mm square. But if you see Kurmi, you will get the answer option number C. But exact answer is option number D, 1500 Newton per mm square. Right? See, as we saw this, the ultimate strength of high tensile steel wires used in prestressing varies from 1500 Newton per mm square to 2350 Newton per mm square. Okay, if you use less than this, then every strength of the steel will be lost by losses in the pre-stressing, right? So you need to have at least this strength. So the cube strength of the concrete used for pre-stressed members should not be less than option number C. So we already saw here, according to Indian standards, the cube strength of the concrete used should not be less than 25 Newton per mm square. So if you see this IS code, you can see here in note 2, for pre-tensioned pre-stressed concrete, the grade of concrete shall not be less than M40, and for post-tensioned it's M35. So pre is M40 and post-tension it's M35. So the answer is 35. So the assumption made in the design of pre-stressed concrete sections that under working load is, so a plane cross section before loading remains plane after loading, and any change in loading produces change of stress in concrete, and pre-stressing in the steel remains constant, and D, all of the above. So you can see the assumption, a plane section before bending remains plane after bending. And next is, within the range of working stresses, both concrete and steel behave elastically, notwithstanding with the small amount of creep which occurs in both material under the strain loading. And again, up to the limit of the modulus of rupture of concrete, any change in the loading produces a change of stress in the concrete only. So you can see here, this is done, right? The sole function of the pre-stressing tendons being to impart and maintain the pre-stress in the concrete, notwithstanding the comparatively small change in the stress of the steel due to change in the strain of the concrete surrounding it. So these all things are correct. So our answer is all of the above. Pre-stressing in steel also remains constant in the assumption. So okay, our answer is all of the above. The cable for a pre-stressed concrete simply supported beam subjected to uniformly distributed load over the entire span should ideally be. So this question was asked in 2080 7th level song, Nepal, right? So the answer is parabolic with, so if you see in the UDL here is acting in the beam, simply supported beam, right? So then so we know that the bending moment of the simply supported beam is like this, right? So it should resemble the curve of the steel's pre-stressing steel should resemble the bending moment diagram, such that it can be effectively used. So our answer is parabolic with zero eccentricity. Let's see, here is zero eccentricity, right? From the centroidal axis, zero eccentricity, and here is the maximum eccentricity, and again here is zero eccentricity. So we can say, and it's parabolic in nature, so we can say parabolic with zero eccentricity at the ends and maximum eccentricity at the center of the span is our answer. Next is, in post-tensioned pre-stressed concrete beam, the in-block zone is the zone between the end of the beam and the section where only longitudinal stresses exist. Okay. Next question. The propagation of a shear crack in a pre-stressed concrete member depends upon the shape of the cross section of the beam. So it depends upon shape of the cross section of the beam. Next is the major loss of pre-stress is caused due to. So major loss is caused due to this A. So this is B, this is C, and this is D. All of these is our answer. Next is the loss of stress with time at constant strain. It's called. So strain is constant, right? So at the constant strain, it is called relaxation. Okay. The losses in pre-stressing systems are due to. So in pre-tensioning system, the losses in pre-stress are shrinkage and creep of concrete. So if the loading on a simply supported pre-stressed concrete beam is uniformly distributed, the centroid of the tendon should be preferably, so it should be parabolic, right? So these two are not right. So and this is also not right. So a parabolic profile with convexity downward is our answer. Next is, in the conventional pre-stressing, the diagonal tension in concrete it decreases, right? So it decreases. The magnitude of loss of pre-stress due to relaxation of steel should be taken to vary from dash of the average initial stress. So answer is our 2 to 8%. Next, according to Indian standard, the total amount of shrinkage for a pre-tension beam is taken as it's 0.0003, right? So let's see. In the absence of test data, the approximate value, this is from IS code. So in the absence of test data, the approximate value of shrinkage strength for design shall be assumed as, for pre-tensioning it's 0.003, that is 3 into 10 to the power minus 4, and for post-tensioning this is the value. So our answer is 3 into 10 to the power minus 4. Next is, at the time of tensioning, the maximum tensile stress behind the anchorage should not exceed. So for the, so let's see here. At the time of initial tensioning, the maximum tensile stress immediately behind the anchorage shall not exceed 80% of the ultimate tensile strength of the wire or bar for steel without definite yield point, and the yield stress for steel with a guaranteed yield point. If there is definite yield point, that is 80%, and if it's not definite, it's not defined without definite, then it's 80%, and guaranteed yield point, for if yield point is definite, then it's equal to yield stress, right? So, and after accounting for all losses due to creep and shrinkage of concrete, friction effects and relaxation of steel, maximum tensile stress at the point of maximum bending moment shall not exceed. So in this case, 60% and 80%. 60% is for without definite yield point, and this 80% is for guaranteed yield point. So in this case, this is for the time of tensioning. So our answer is, this 2 is for after all the losses, right? So this and this, let's see this, after accounting for all the losses, these 2 questions are the answers of this thing, and this below to 80% is the answer of this particular question. So 80% the ultimate strength of the bar for steel without a definite yield point, and next is the yield stress for steel with guaranteed yield point. This is at the time of tensioning. Next is, for pre-stressed structural elements, high strength concrete is used primarily because of high modulus of elasticity and low creep. So we need to have high modulus of elasticity, right? But we require low creep. So if so why do we need high strength concrete? Let's see. First number, since large stressing forces are applied to the member by the tendons, so P is high, right? Pre-stressing force is high. And high bearing stresses are developed at the ends of the anchorage devices. So bearing stresses are also developed. Bearing stresses. The anchorages are generally designed to be meant for use only for high strength concrete. So the anchorage bearing strength should be high in high strength concrete, right? High strength. Otherwise, it will not sustain the load, right? So next is bursting stresses liable to at the ends of the beam cannot be satisfactorily resisted by low strength concrete. So to withstand bursting stress, so we need to use high strength concrete as well. So third number, when the stress transfer to concrete has to take place by bond action, the concrete should have high bond stress. So to get the high bond stress, high strength concrete should be used. Again, next 4 number, shrinkage cracks will be very little when a high strength concrete is used. So high strength concrete gives less shrinkage. So this is also one of the point. And next is, due to high modulus of elasticity of high strength concrete, the elastic and creep strain are very small, right? So loss will be small. So our answer is high modulus of elasticity and low creep, which causes lesser loss, right? When the tendons of rectangular pre-stressed beam of cross-section A is subjected to the load W through the central longitudinal axis of the beam, then so this is missing something here. Okay, I think so. But the answer, according to the options, the answer will be, so if this is a cross-section of the beam, and in the beam, if P is applied as load, P is the pre-stressing force, P is pre-stressing force, Okay, you can see here stress due to pre-stressing force, uniform, right? This is uniform. And if this m by z is due to load, right? External load. So pre-stressing force is uniformly distributed, and the stress due to bending moment is like in this shape. So in this case, if we add this and this, we will get P by A plus M by Z, here maximum, and here minimum P by A minus M by Z. So in this case, it is asked maximum, so we will go for, in the case of P, it's W, right? W by A plus M by Z. Similarly, in the previous question, if you are asked to show the minimum stress, so our answer will be W by A minus M by Z. The diagonal tension in a pre-stressed concrete member will be less than, shear stress. When a pre-stressed rectangular beam is loaded with uniformly distributed load, the tendons provided should be parabolic with convexity downward. Yes, true, right? This in this way, right? That resembles the bending moment diagram. So let's go. In the Lee-Mackel system, low alloy steel bars are used as the pre-stressing tension. No, we need to use high alloy steel bar. So we will disagree this statement. Now next, it is required to completely balance a bent tendon of span L carrying a point load W at the center. The minimum central dip should be equal to, so we need to calculate central dip, right? So this is the this is a beam, and W is applied at L by 2 at the center, and H is the dip, right? This is the dip, and theta is taken as this theta, this is theta, right? So the pre-stressing force, so this is the pre-stressing force, and now P sine theta, right? So this is P sine theta, upward force is P sine theta. Since the theta is small, we can consider sine theta is equal to tan theta, right? So if the sine is sine theta, then so how can we calculate this? Tan theta, this is L by 2, right? This is L by 2, and so tan theta will be P by B, right? So H by L by 2, so 4P H by L. Now this pre-stressing force will generate the upward uniform upward force. So 4PS should balance this W, right? So 4PH by W equals to 4PS by L equals to W, right? Now H equals to WL by 4P. So this is a quite simple derivation. So you can calculate H central dip as WL by 4P by balancing the pre-stressing load and external load. So our answer will be WL by 4P. Now a simply supported concrete beam pre-stressed with the force of 2500 kN is designed by a load balancing concept for an effective span of 10 meter and to carry a total load of 40 kN meter, right? So in the case of parabolic, H equals to WL square by 8P. You can calculate this. You can also derive this, but I am writing this directly. So H equals to WL square by 8P. So what is W here? W is 40 load, right? And P is pre-stressing, right? 10 square by 8 into pre-stressing force is 2500, right? If you calculate this, it will be 0.2 meter. 0.2 meter is 200 mm, right? So this is our answer. Next, pre-stress is imparted to concrete by bearing in. So let's see. So for the post-tensioning, so post-tensioning is a method of pre-stressing concrete by tensioning the tendons against the hardened concrete. So it is done after the concrete is hardened, right? By providing docks and then grouting it after providing the tensioning, right? So in this method, the pre-stress is imparted to concrete by bearing. So in this method, we need to have a proper bearing in order to transfer the anchor this effectively and do not affect the concrete, right? So the answer will be, our answer will be post tensioning. Next is the minimum grade of concrete for free tension member is, so for pre-tension member, right? Not post tension member, pre-tension member is M40. So for note 2, for pre-tensioned pre-stressed concrete, the grade of concrete shall not be less than M40. Okay, the mixed proportion of cement mortar to be used in joints in precast pre-stressed member is 1:1.5. The diameter of the high tensile tendons used is 5 to 8 mm. Now the minimum clear spacing for single wires. So here is single wires, right? So it has to be, let's see. So for the spacing, this is from IS code, and what does it say? So in the case of single wires used in pre-tension system, the minimum clear spacing shall not be less than the greater of the following. So what are they? 3 times the diameter of wire and 1/3 times the maximum size of aggregate. Let's see, 3 times the diameter of the wire and 1/3, right? So it's near to 1.5 times the maximum size of aggregate, whichever is greater for the single wire, right? So the minimum clear spacing of non-group. So it's asked for non-group. Let's see. So in the 2 number, so in the case of cables or large bars, the minimum clear spacing shall not be less than the greater of the following. So what is this? 40 mm maximum size of cable or bar and 5 mm plus MSA, right? Maximum size of aggregate. So 40 maximum size of cable, 5 mm plus MSA. So you can see 40 maximum size of cable or bar, 5 mm plus MSA. So greater of A, B and C of above is our answer. Now again, the minimum clear horizontal spacing between the group of cables or docks of a grouped cables shall be greater of. So it's asking about group cables, right? So for the group cables, let's see. For the group cables, so cables or docks may be grouped together in groups of not more than 4, right? So the minimum clear spacing between groups of cables or docks of grouped cables shall be greater of the following: 40 mm or 5 mm plus MSA, right? Maximum size of aggregate. Let's see. So 40 mm for the group cables, 40 mm or 5 mm more than the maximum size of aggregate. So what did we learn? So we learned about the single wire system, right? So 3 times the diameter of the wire in 1/3 times the maximum size of aggregate. And for the ungrouped wires, right? So for the ungrouped wires, 40 mm or maximum size of cable or bar or and 5 mm plus MSA, right? So again for grouped cables we studied 40 mm. So this is 40 mm or 5 mm more than the maximum size of aggregate. Next is the minimum clear vertical spacing between. So it's asking about vertical spacing in grouped cables, right? So it will be, so let's see here, the vertical distance between the groups shall not be less than 50 mm. So our answer is 50 mm. The grouting of docks in pre-tension pre-stressed concrete causes reduction in deflection, reduction in crack width, reduction in corrosion, all of the above. So our answer will be all of the above. A parabolic tendon in pre-stressed beam causes an equivalent balancing what? UDL. So the equivalent balancing UDL, we already talked about this. Next, an increase in stress in concrete member at constant stress is called. So it's, if it's constant stress and the strain is increasing, then it is called what? Creep loss, time dependent loss, right? So strain in concrete at zero stress. So if it's the stress is zero, it is shrinkage, right? Shrinkage. Even if the stress is zero, there can be strain in concrete that is caused by shrinkage. In case of pre-stressed concrete, pre-stressing force is compressive stress. So we introduce artificially compressive stress in the structure, right? So our pre-stressing force is compressive force. In case of pre-stressed concrete, load carrying capacity of member increases, quantity of concrete is saved for safe grade, quantity of steel is saved for same grade, all of the above. So all are correct, right? So the same design load, the weight of concrete in a pre-stressed concrete as compared to ordinary reinforced concrete is less by 50%. Next is a pre-stressed concrete member. Option number A is made of concrete. Option number B is made of reinforced concrete. C is stress after casting, and D is possesses internal stresses. So pre-stressed concrete possesses what? Internal stresses. So a pre-stressed concrete member is a member of concrete in which internal stresses are introduced in a plain manner so that the stresses resulting from the superimposed loads are counteracted to a desired degree. Next, In favorable circumstances, of 15 centimeter concrete cubes after 28 days attains a maximum crossing strength. So if we study here, while it is not difficult to make concrete which can have a crossing strength of over 400 kg per centimeter square or 40 Newton per mm square on 15 centimeter cubes after 28 days curing, it is difficult to obtain a tensile strength greater than 25 kg per centimeter, 22.5 Newton per mm square. So this is why concrete is reinforced with steel bars in such direction where tensile resistance have to be offered. So in this case, we are the answer is 400 kg per centimeter square. Next question. So a prestressed concrete member is preferred because its dimension are not decided from the diagonal tensile stresses. And next is a large size of long beams carrying large shear force need not to be adopted, and removal of cracks in the members due to shrinkage. The option number D is all of the above. Let's see here. So if we see here, the dimensions of these are the weakness. These are provided as the weakness of the RCC member. The dimension of the member may also have to be determined from diagonal tensile stress considered. So this is all for RCC, right? Not for PCC. So these problems are PSC, prestressed concrete. So these all things are not found in PSC. So you can see these are found in, this problem is found in RCC. In the case of long beams where large shear force exists in the beam size have got to be large to limit the diagonal tensile stress under certain limits. A reinforced concrete member is also found to develop cracks even in the sense of load due to shrinkage of concrete in the hardening stage. So these are the problems of RCC. So this can't be found in prestressed concrete members. So our answer will be what? All of the above. So we don't have to take care of these. So the dimensions are not decided from the diagonal tensile stresses, and large size of long beam carrying large shear force need not be adopted, and removal of cracks in the member due to shrinkage. So next is, in a prestressed member it is advisable to use. So what is this? The answer is high strength concrete and also high tensile stress. So why high tensile stress? In order to account for the losses, right? If not high tensile stress, all the strength of the steel will go on losses, right? So next question is, so we have already discussed about this. The minimum cube strength of concrete used for a prestressed member is 350 kg per centimeter square, that is 35 Newton per mm square. High strength concrete is used in prestressed member. Why? Because to overcome high wearing stress, right? To overcome bursting stress at the ends, to provide high bone stresses, right? And to overcome cracks due to shrinkage. All of these above. So we can see here, we have already discussed about this. Let's go to the next. Pick up the assumption from the design of prestressed concrete member from the following. So assumption given as, a transverse plane section remains a plane after bending. Yes. During deformation limits, Hooke's law is equally applicable to concrete as well as steel. Yes. And variation of steel in reinforcement due to changes in external loading is negligible. Yes. So our answer will be all of the above. So if you see here, this is the assumption in the design of prestressed concrete members. So a transverse plane section of the member will remain a plane after bending also, and within the limits of the deformation taking place, Hooke's law is applicable to concrete and steel components as well. And the stresses in the reinforcement does not change along the length of the reinforcement. Stress changes take place for the concrete component only, and variation of stress in the reinforcement due to changes in the external loading is ignorable, right? So next, if A is the sectional area of a prestressed rectangular beam provided with a tendon prestressed by a force P, so if there is a rectangular beam with prestressing force P through its centroidal longitudinal axis, if the P is applied at centroidal longitudinal axis, then the compressive stress in the concrete is what? It's just P by A. You can see here, if this is the beam and this is the force applied, then let P be the prestressing force applied by the tendon, and due to this pre-stressing force, the compressive stress induced in the concrete is P by A. So if this is P and this is P, then the compressive stress induced is uniform, and it's P by A. So it's like this, right? Like this, uniformly, right? P by A. So and if due to the dead load and external loads, the bending moment at a section is M, then at the extreme cases at the section, due to the bending moment, M by plus minus M by Z, right? So if we have already discussed about this also, so if it's asking for maximum bending moment, then it's P by A plus M by Z, right? This one. So P by A is due to pre-stressing and M by Z is due to external load and dead load, right? Next, so you can see here P by A due to pre-stressing force and M by Z due to bending moment. And here maximum is here P by A plus M by Z, and minimum is here, right? So next is, so here it's asked as minimum stress, so we can say P by A minus M by Z. Okay, so calculation of final stresses in the extreme fibers of a pre-stressed rectangular beam, step by step graphically is shown in this figure. State whether figure 1 is wrong, figure, so which figure is wrong, we need to say, right? So for this, let's see. So if this is P by A and this is due to M by these are M by Z, right? So it's okay, it's right? So this is uniform pre-stressing force, and this is positive and toward this direction, right? And this is never negative, and this is towards this direction. So we need to add here, right? So you can see here you need to add P by A plus M by Z. So 40 plus 40 is 80, right? So this is correct, and here we need to subtract, right? 40 minus 40 is 0. So all of these are correct and none of the figures is wrong. Next question, if the tendon below the centroidal axis, if this is centroidal axis of the beam, then tendons are placed where? Here, right? At eccentricity of E. So this is talking about this. And the stress at the extreme top edges. So what will be the stress in the extreme top edges? Let's see. So this is the eccentricity E and the tendons are placed here, right? Now let's see, due to pre-stress it's uniform, right? P by A, and due to eccentricity of the pre-stress it's P by Z minus here and plus here, and due to external bending moment, so external bending moment plus here and minus here. So at the top it is decreased by what? PEZ, right? It's decreased by PE by Z at the top, right? So we can say for the particular question we can say it is decreased by PE by Z. So it was, if it was not placed at the eccentricity, it will be only P by A plus M by Z and P by A minus M by Z. Now it is decreased by PE by Z since it's in is provided in at eccentricity, right? Next question is calculation of final stresses in extreme fibers of the pre-stressed rectangular beam having a tendon placed at an eccentricity E below the centroidal axis graphically is shown here. So this is correct, this is uniform P by A pre-stressing stress, and for this PE by Z, so if you see this PE by Z, this has to be in this direction, right? Because you can see here positive is in this direction, so this has to be negative, right? So and this has to be positive. So we can say these all things, this is correct and this is also correct, but this particular figure is not correct. So we can say that figure 3 is 1, 2, 3, right? Figure 3 is wrong. Okay, you can also see here the negative direction is this side and positive direction is this side. Next, so in a pre-stressed beam carrying an external load W with a bent tendon is having an angle of inclination theta, in the pre-stress load P, the net downward load at the center is, so if you see this figure, so this is the beam and W is applied here, and this is the bent tendon and the angle is theta degree with horizontal. So this has to be theta degree also, right? This has to be theta degree, and this P will produce uniform upward force, right? So uniform, if it provides uniform upward force, it will be P sine theta from here and P sine theta from here, right? This one. So it will be 2P sine theta, and this is in downward direction and this is in upward direction. Then the downward load at the center will be W minus 2P sine theta from the equilibrium condition, right? So our answer will be W minus 2P sine theta. Where is W minus? Oh, here is W minus 2P sine theta. Next is, if the loading on a pre-stressed rectangular beam is uniformly distributed, the tendon to be provided should be. So if it is uniformly distributed, then tendon should be like this, right? Parabolic and convexity downward, right? So our answer will be parabolic with convexity downward. Next, if the maximum depth of a parabolic tendon carrying a tension P is S and the effective length of the pre-stressed beam is L, upward uniform pressure will be. So we have already discussed about this. H is equal to, so WL is square by 8P, right? So in the case of W will be what? 8PH by L square, right? So our answer will be 8HP by L square. Okay, this is the figure to understand. And here is the horizontal reaction at each end of the cable will be WL square by 8H, and this has to be equal to P, right? So it has to be 8HP by L square. The P is 8HP by L square. Okay. Next, if a bent tendon is required to balance a concentrated load W at the center of the span L, the central dip H must be at least. So in the case of this, we have already talked about this as well. WL by 4P is the answer, right? You can pause and read the content. So a pre-stressed rectangular beam which carries two concentrated load at L by 3 from either end is provided with a bent tendon with tension P such that the central 1/3 portion of the tendon remains parallel to the, so central 1/3 is parallel, right? And remains parallel to the longitudinal axis. The maximum dip H is, so the process is same. You can see here and pause the video and you can derive yourself. So this is very easy to derive, and it comes out to be that central dip is WL by 3P. So WL by 3P is here, right? So our answer is WL by 3P. So WL by 4P in case of central load, WL by 3P in case of the load, two loads at L by 3 from the end, right? So next question is, the system in which high tensile alloy steel bars, silica manganese steel are used as pre-stressing tendons is known as. So this is Lemakel system. So in this system, high tensile alloy steel bars, silica manganese steel are used as the pre-stressing tendons. So this is also important question. So next is, if K is Oval correction factor and mu is coefficient of friction between the docked surface and the curve of tendon of radius r, the tension ratio at the distance x from either end is, so this is from loss. So loss of pre-stress during the this is for the during the tensioning process due to friction. So they are of two types: loss due to length effect and loss due to curvature effect. So if you see the loss due to length effect, so the pre-stressing force Px in the tendon at any distance x from the jack is given by this formula: P naught E to the minus K C, right? So P naught is pre-stressing force at the jacking end, and K is a coefficient called Oval correction factor. Kx, this is Kx, this is Kx, and this is Px. The tension at any point of the cable is given by. So this is this first one is due to what? Due to length effect, and this second one is due to curvature effect. Curvature effect. Px is equal to P naught E to the power minus mu x by r. So if it is usual to combine the length effect and the curvature effect, and the tension in the tendon is given by. So if we combine this will be the equation. Now we also know that e to the power minus x is can be written as this, and if we neglect this higher power, then we will only get what? Px is equal to p naught 1 minus kx minus mu x by r, right? So this particular quantity is known as tension ratio. So what is tension ratio? It's 1 minus kx minus mu x by r. So our answer will be 1 minus kx minus mu x by r, option number C. Next is, after pre-stressing process is completed, or loss of stress is due to. So these losses are loss of pre-stress occurring subsequently after the pre-stressing process is completed. These 4 losses will be there, right? So loss of stress is due to shrinkage of concrete and creep of concrete, elastic shortening of the concrete, and creep of steel, that is stress relaxation. So all of these will be there, right? So our answer is all of the above. Next is, if C is the creep coefficient, F is the original pre-stress in concrete, M is the modular ratio, E is the Young's modulus of steel, and E is the shrinkage strain. The combined effect of creep and shrinkage is, so the loss of pre-stress due to creep is given as C minus 1 and M F, right? This is due to what? Creep. So due to, and again due to strain, due to shrinkage, it will be strain into what? Strain is written as this, strain into elastic modulus. So if you combine this C minus 1 MF and EE, so we will get what? C minus 1. So this is the answer. C minus 1 MF plus EE is our answer. Next is, if MD and MT are the maximum bending moments due to dead load and live load respectively, and F is the total effective pressure for a balanced design of a pre-stressed concrete beam of steel. So the book has given this formula. So this is MD by P plus MT by 2P, right? So this is given in the book, but the answer is given as different. The answer is given as, sorry, this is L in this case, right? So the answer is given at E is equal to MD by 2F and plus ML by F in the book of the Augur book. The answer is given as B in the Augur, but it in the textbook it is as this. So this will be similar to this, right? So in the Augur it is written as this, and in the book it is written as this. As per IS 1343, the total shrinkage for a pre-tension beam is 3 into 10 to the power minus 4, right? So option number C is our answer. So you can see here 0.0003. Next, post-tensioning system, option number A, was widely used in earlier days. No. Is not economical and hence not generally used. So it is not generally used in the general cases, right? So it is quite not economical as well. So and is economical for larger spans. So in the as compared to pre-tension, it is economical, right? It is economical, but normally it is not that economical. So it's economical for large spans and is adopted nowadays. So this is also the correct answer, right? But the book of Augur has given the answer as none of these above. So if you see here, pre-tensioning system was widely used in earlier days. So this is not correct, because in the earlier days a pre-tensioning system were used, right? And these pre-tensioning systems are found uneconomical for larger spans as well. So the answer should be I think C, but the answer is given as D. Next is, the ultimate moment resisting capacity of a simple supported pre-stressed concrete beam is obtained by using. So also in this case, according to Byju's, the answer is option number B, but according to the book of Khurmi, the answer is given as A. Next, in pre-tensioning pre-stress is transferred in. So also in this question, according to Khurmi, the answer is multi-stage process, but according to Byju's, it is single stage process. So it is quite confusing, and you guys decide and comment in the comment section about these 3 questions. This is first one, comment down your answer, and this is the second one, comment down your answer, and for this also comment down your answer. And that's all for today. Thank you for watching.